let us next discuss the graph of the remaining three trigonometric functions, secant, cosecant, and cotangent. And this, we're going to take a much shorter approach because this lecture is already getting way too long. But let's just use our calculator to graph them from here on out. So what's kind of key to remember about the other three functions is, well, always reverting back to what is their definition. If I'm trying to figure out what is cotangent, what does this look like, and how do I understand it, we need to always revert back to the unit circle. So cotangent, much like tangent, was defined to be x over y. So if I was to do, well, what's the cotangent of a particular t position on the unit circle, given by x over y. And note that it's the exact reciprocal to tangent. Or another way to remember it was by the reciprocal identity, which is that tangent of t, just recalling, was y over x. Cotangent was the flip. So if what this implies is that if I wanted to graph cotangent of t, it's the same as 1 divided by the tangent. Because the tangent always produces I don't believe we got into this, and we will get into this into a later video, but I wanted to just mention, for how do I plug it in my calculator if I wanted to do this? Because really the other three are not buttons that we have. We only have sine, cosine, and tangent. We don't have the other three accessible on our calculator's menu. But tangent is y over x. But basically, how do you do it is by this, what we call the reciprocal identity. If you just type in 1 divided by tangent, that is exactly the same as cotangent. But I wanted to mention why before I use it, because I don't like to teach you guys anything without discussing why it's true. But tangent, since tangent is y over x, notice that if I take the reciprocal of y over x, that will, since I'm dividing by it, it will flip back over 1 times x over y. But notice that that's consistent with the definition of cotangent. So cotangent is always created by reciprocating tangent. But if I want to look at the graph of it, that's what I need to type in. So if I type in 1 divided by tangent x, again, we're using x because that's how our calculator, the variable our calculator uses to graph functions in general. Instead of using t, that's just, we use that because that is helpful to understand what it means from the unit circle. What we see is cotangent looks very similar to the tangent graph that we just did. It's just going the other way. And also the asymptotes are at different locations. So if we look at this, and this to remind you, is in the trigonometric window. So this is 0, pi, 2 pi, negative 2 pi in each of those normal iterations. But the tangent, I'm just going to graph it on the right side. Its vertical asymptotes actually occur at 0 and at pi and at 2 pi, as opposed to occurring at pi over 2 and 3 pi over 2 as they did with tangent. But basically it has different vertical asymptotes. It's also going the opposite way because it's the reverse ratio, which just flips the graph, really. And where it actually has its x-intercepts, or its roots, are right in the middle, pi over 2 and 3 pi over 2. And if you check it by evaluating all of those things, you'll see that the cotangent is undefined at 0, pi, and 2 pi, meaning you can't plug it in. But if you say do the cotangent of pi over 2, that will indeed produce 0 if you follow through with the unit circle. Now let's move on to cosecant and secant. But if you're wondering, like, what would I possibly test you on all of this? There's so much information. I want you to know the basic shapes of them all, and I want you to know how to take sine and cosine and perform transformations on them all. So, I mean, really my goal is to help you understand all of the intricacies of these graphs, but also without getting into such fine detail because ultimately I don't view most of this as important. I do think all of the stuff with sine and cosine is, especially for those who ever want to study signal analysis or really advanced music. But the other one, so reviewing back to cosecant and secant, as I discussed way a long time ago in chapter back in 4.2, cosecant is the reciprocal of sine, secant is the reciprocal of cosine. Since cosecant was defined to be 1 over y, it's equivalent to when looking at the unit circle, not standard view of y. That's always equivalent to 1 divided by the sine, because sine of t is always, again, I'm using x here, so actually I don't like what I'm doing. I'm just going to erase this and do it based on our unit circle definitions. Recall that cosecant of t was defined to be 1 over y when we're talking about the unit circle, which is the same as 1 over the sine of t, since sine of t was defined to be y. So if I'm trying to graph a function, again, x doesn't mean anything. It doesn't have, with relation to the unit circle, just a general variable. Cosecant can be graphed by simply graphing 1 divided by sine. So let's go ahead and do that. Y equal 1 divided by sine, which is the cosecant function. And if I hit graph, we can check out what it looks like. And notice that this is sort of like an inverted, it looks sort of like an inverted sine wave. Instead of being a normal wave that's bouncing up and down, it's actually like it's exploding up to infinity, because it also has vertical asymptotes like tangent and cotangent, but it's sort of stuck in between them. Instead of going back and forth, it's right in between. So let's go ahead and sketch this out, excuse me, on the whiteboard and discuss the location of the asymptotes, which again helps us to see the domain. But notice that with cosecant, the asymptotes are actually at exactly the same location as the cotangent, which occur at 0, pi, and 2 pi. And I'm just getting that from looking at it, but again, you can see why those make sense by looking at the unit circle. And back to, well, where is sine 0? Because you can't divide by 0. It's not going to work at 0, because sine of 0 is 0. You can't do that. So there's an asymptote there. Same, sine of pi is also 0. Sine of 2 pi is 0. So the cosecant is undefined at each of those spots. And then in between it, between 0 and pi, we have this sort of cup shape. And then between pi and 2 pi, it's got the upside down cup shape as well. And one thing that I thought I'd mention is that the very minimum point of the cosecant function is actually the halfway point, pi over 2 and 3 pi over 2, those very specific points, which is also 1. Since if you recall, and actually let me actually sketch a typical sine wave in between this, because you can kind of see the connection between cosecant and sine if we're trying to view the reciprocal property. Well, sine of 0 is 0. So when we reciprocate 0, you get an undefined value. It goes up to infinity. But at pi over 2, sine made 1. Well, the reciprocal of 1 is 1. So what we get is they actually are the same point, which is what that minimum point those cups are. Like if I'm looking right there at my graph, notice it's exactly on at 1. And then when we get to pi, it goes back to being undefined, because sine is again back to 0. Then when we go down to -1, the reciprocal of -1 is -1. So we're still there. And then when we get to 0, we get undefined. But my whole point here is, how would you memorize or remember all of this stuff? If you know your sine, all the properties can be extrapolated, because this is simply the reciprocal function. And same with secant. Let's actually try to do secant without looking at our calculator. But in the same way, you could graph secant by doing 1 over x, because going back to our definition, secant of the terminal position, or of the distance to the point, was always equal to, defined to be 1 over x on the unit circle, which is the same as the cosine, right? Because cosine is x, sine is y. And those are those two keys. But basically, if we want to use our calculator, we could always just graph 1 divided by cosine. Cool, that's always equivalent to the secant. But basically, if I start off, let's do the same thing I did before. Let's start off with a cosine graph, and we'll use our reciprocal idea to sketch it. Cosine started at 1, came down to 0, went down to -1, back to 0, and up to 1 in its original form. And also, just to mention, blue is not the graph. Like the graph, of the cosecant is just the part in black. The blue is sort of just like a visualization secondary curve. I can go ahead and write that. Let me just note that this is the graph of sine. And in this case, what I'm graphing currently is cosine x. And since secant is the reciprocal, instead at 1, the reciprocal is 1. And instead of going down to 0, it will blow up to infinity. And the vertical asymptote will be at the point where cosine intersects the axis. And below, it will be reciprocal of each of the negative values, which will go down like that. And again, head towards this vertical asymptote. And by the time I get back to 2 pi, which again, since the standard period of sine and cosine is 2 pi, note that secant and cosecant also have periods of 2 pi. It actually says all that in your packet, which I'd recommend kind of looking at all that stuff. But note that note that all the trigonometric functions have periods of 2 pi except for tangent and cotangent. Those happen to repeat their cycles more rapidly just because of the nature of them being ratios of x to y and y to x, as opposed to just 1 over x, as those would be. But also, if you look at the graph of secant in the calculator, instead, notice that it's the same. Again, it's the same graph as, just like how sine and cosine are really the same thing. They're just phase shifted. Same with secant and cosecant. They're the same graph. They're just moved over by pi over 2, which is also why they're called cofunctions. So notice the similarity between secant and cosecant, tangent, cotangent, sine, cosine. Each of the cofunctions have the same graphs. They're really the same thing. They're just off. They're actually, it has to do with complementary angles. When we get into triangles, we'll return to that idea, which again, a lot of people aren't really aware of all that. But this wraps up our discussion on sine on the other 4. And if you want to expand it, you can do all the same transformations that we did before, where in this case, this would affect the vertical shift, this would affect the period, same with secant, by using these formulas here to solve those things. But you can also graph them in your calculator to check it out. And that will wrap up this video.